Okay, this is the video recording of Unit 4, Lesson 4.5. All right, so we're going to talk about stretching functions vertically. All right, so we talked about moving them earlier today. Now we're going to talk about actually this thing called stretching them. So for the overview here, it's referring to stretching things or compressing things in relation to a funhouse mirror. Okay, so that's a way that you can think about this, is distorting the shape of the different graphs here. And so again, we're gonna work with that, and how do we actually do that graphically, and how do we do that using our equations. All right, so for the study here, okay, again, it's talking about starting with credit cards, right? Saying that basically you can encode or encrypt credit cards, and that's how, when you type in your code, that people don't just automatically get your information. All right, but basically how that relates to algebra is that we can do this to functions as well, right? We can encode or change the shape of the graphs, and really, again, make the graphs look the way that we want them to look, and understanding how to go back and forth from there. Okay, so if we look at this graph here, okay, the red graph is stretched vertically, right? So vertically, again, being up and down. And if you look at the difference here, really, they're at the same x value, but really what's changing is those y values, right? And if we look even here, okay, again, the y values are the ones that are changed, and it actually looks like, since we have those coordinates, the y value is twice as much as the original here. And so we know that the outputs of our new equation g of x, right, that red equation g of x, are 2 times as large as the outputs of our original f of x. Right, so we know that it's going to be 2 times larger. And what we can do with that, since we know that it's going to be 2 times larger, we can actually multiply f of x by 2 to find this equation. So again, we know that g of x is twice, it's got an output of twice as large. So what we can do is, we can multiply the entire equation for f of x by 2. So again, it looks like 2 times f of x because it's twice as large. And then what that looks like then is, we have 2 parentheses x squared minus 3x, right? And then we've got to distribute that 2 out. So our new equation here actually has an equation of 2x cubed minus 6x. All right. And again, that is solely based on the fact that we were able to look at the coordinates and realize, hey, it's not moved left or right, up or down. It's actually stretched. And one of the reasons we can know that is because the points haven't shifted, right? They're just slightly elongated on that xy coordinate there. Okay, so then we can see again how we can vertically stretch by multiplying the right hand side of the equation. We can also compress the graph in a similar way. Okay, so if we look here, we've got one of those sliding tools. So if I pull this really large, all it's going to do is start pulling that graph, really stretching that graph out. Same thing if I start to compress, I am now at numbers less than 1 but greater than 0, okay? And I've actually flattened out, okay? I flattened out those curves, or compressed those curves. And if I keep going here, at some point you're going to notice at 0, I make a straight line, okay? Obviously, because anything multiplied by 0 gives us 0. But when we start having negative, you can see that the graph really changed there. And we'll talk a little bit more about that moving forward. But you can notice here that when I get above 1, it still looks like I'm stretching that graph. Okay. So in general, though, anything above 1, right, above 1, positive 1, or negative 1, okay, anything larger in those directions, okay, is going to give us this stretching function. Anything between 0 and 1 is going to result in this compression. Anything between 0 and 1, or 0 and negative 1, is going to result in this compression. Okay, so again, this is just reiterating what I just told you. Okay, so if you have a number greater than 1 or less than negative 1, you vertically stretch the function, okay? And when you have a number between 1 and negative 1, you compress that function, right? Or push it down. And again, with the exception of 0. So if we're looking at this, vertically stretching, okay, we're pulling apart. Vertically compressing here, right? Pushing that together. And even if we look here for negative numbers, okay, negative numbers, yes, we are flipping, and we'll talk about that in the next slide here, but we are pushing down on that graph versus when we stretch it, even though it's opposite, right, we are vertically pulling that when we stretch. Okay, so then again, here's talking specifically about multiplying by a negative number. So what we're going to notice here is I can go and make that number larger, and I'm going to stretch. Basically, if I hold it at that axis, I'm going to pull that upwards. And the one I think of is like taffy, right? I pull it up like taffy. It makes the taffy thinner. But if I start going slowly here and I start multiplying by lower numbers, okay, I'm starting to vertically compress. I have 0, and then what you're going to notice here is that I do the same thing, but on the other side of that x-axis here. So what this ends up doing is that we end up flipping over the x-axis. So when I multiply by a negative number, right, when we multiply by a negative number, we flip over the x-axis, right? And then depending on if that number is smaller than -1 or between -1 and 0, that's going to tell you if after you flip across the x-axis, are you stretching or are you compressing? So for example here, I flip, at 0, right? I flip, I'm compressing, back to normal, stretch, right? So if I multiply by -1, if I multiply by just -1, it's like I'm just flipping over the x-axis, right? I'm mirroring across the x-axis. But it's as soon as I get smaller than -1, I start to stretch again. Okay, looking back at this, when you multiply by a function, a negative number, again, it flips over the x-axis, and that's because the output, right, so your y values, after you've calculated them all, right, they just flip the negative sign, right? They flip the sign. So here I've got 2, 4, right? So if x is equal to 2, I'm going to have 2 squared, and then that's going to become the negative of that, right? So I'm going to have the negative of that, which is 4. And let me clarify here, there is a difference between negative x squared and parentheses negative x squared. And by that, I will show you here using my calculator. So pause for 1 second while I pull that up. Okay, so what I mean by that is there is a difference between having negative x and having that quantity squared, right? There's a difference between that and what we're talking about is negative x to the power of 2, right? So for example, if we're looking at that first one, negative x and then squaring that, that would be like saying -4, right? -4 to the power of 2, right? That's going to give me 16. But if I do negative, right? If I do -4 to the power of 2, that's going to give me -16, because what it does is it does order of operations. So it'll do that 4 squared first, which gives you 16, and then it will take the negative of that answer, right? So we've got to make sure that when you're looking at this, you're realizing that it's totally different, right? And again, that's where parentheses and being particular with what you mean is going to come in handy. All right. So if we keep moving forward here, though, that's talking about changing those output values, right? So again, you're still plugging in 2, and you'd get 4. Okay, so if this is just f of x is equal to x squared, right? I don't know why there's a negative sign there, right? This is our parent function. Okay, so this is f of x equals x squared. So that should be, if I plug in 2, I get 4. All right, but then when I have g of x, again, I plug in 2, so I have 2 squared, then I take the negative of that, so I would get -4 there. All right, so then moving forward here is what happens to a function in order to get it to flip over the y-axis. What happens there? All right, and what we can look at here is if I zoom in, there's 2 examples. So if this is my original function here, okay, f of x is equal to x plus 4 and then cubed. If I want that to flip over my y-axis here, if I want that to flip over my y-axis, what I just do is I have a negative x value instead, right? So So I change the inside quantity of x. All right, so I change the inside quantity of x rather than the entire equation itself. All right. Again, both of these are based on that parent function of just x cubed by itself. So x cubed would be up here into the middle. So what it's saying is when I look at this equation here, all right, this one is telling me, all right, move 4 to the left, then we're going to have that x cubed relationship. Okay, what this one's telling me here is that, okay, we're going to move 4 to the left because of that plus 4 there. We're going to move 4 to the left, and then we're going to reflect it across the y-axis. And then again, we're going to have that squared functionality there. All right, so when we flip across the y-axis, all of the y values will stay the same. Okay, the y values will stay the same, but what changes will be the x values. Okay, what will change will be the x values. All right, so when you flip a function horizontally, you flip it over the y-axis, okay? So that means it's multiplied by a negative number. All right, so again, I now have negative x cubed plus x instead of x cubed minus x. Right, so when you flip a horizontal function, right, when you flip it horizontally across that y-axis, it's multiplying the x value by a negative number. All right, so a couple examples here of stretching and compressing. So if we look at our parent function of x cubed, all right, in order to say that it is stretched vertically by a factor of 3, we would say 3x cubed. All right. And if it's stretched vertically by a factor of negative 2, right? If it's stretched vertically by a factor of negative 2, again, you put the entire function in parentheses, and then you multiply everything by that negative 2 factor, right? And remember, if we have a negative 2 out here, that means we are going to flip across our x-axis. All right, and then lastly here, compressing by a factor of 0.5. So we would put 0.5 and multiply that out throughout the entire function. Okay, so now we can combine everything we learned in the last unit in 4.4 with this new unit. So we can now stretch, compress, and shift all at the same time. So if we look at our base function here, our x squared, okay, we can shift 2 units up, right? 1, 2, and then we can shift 6 units to the left, right? So we should be able to do that now. Okay, so again, we add 6 because we're moving to the left inside our x squared component, and then we add 2 to the outside of the function because we are moving up 2. Okay, now when we're going to flip across the x-axis, okay, we need to flip and then we need to shift 3 units down. So we flip and then shift 1, 2, 3. Okay, so what you're going to notice is we now have negative x, right? So we have negative x squared because we flipped across the x-axis, all right? And then we still subtracted 3 because we moved downwards, all right? And each of these examples below, right, it is shown in red from the parent function in black. And again, these are a lot of really good examples for you to be able to relate it to, okay, what is it saying in equation form? What does that look like on a graph? And how would I say this in English, right? And a good way of looking at this is doing the steps in the order that you maybe see them, right? So vertically stretching by multiplying by 3. Okay, well, you see that there's a factor of 3 there. Okay, so this is no longer just x squared. It's now 3x squared. All right, but then we're going to shift 2 units to the left. So it's no longer just x. You've got x plus 2, so that's within inside the quantity. And then if we shift 7 units up, we're going to add 7. Okay? Or we could work the other way. So if we start with this guy, shift 1 unit down. So that would mean that's x squared minus 1. Okay? We want to shift 4 units to the right. So now it's x minus 4. Then that quantity gets squared. And if we want to vertically compress it, we then multiply it by that 0.2 factor. We multiply it by that 0.2 factor. And what you want to notice here is whether we're multiplying in order to stretch or multiplying to compress, okay, the factor that we multiply only deals with our x terms, okay? It leaves the constants on the outside and inside alone, okay? You multiply by the outside, and then if we were to carry this through, we would then distribute, okay? So you leave as is and then distribute once you are done adding in all of these shifts and stretches. Then you would simplify further if needed. Okay, so vertically stretching and compressing functions changes the shape of the function's graph. So it actually does now change the shape of the graph. It's no longer just moving up and down. Okay, in order to vertically stretch, we need to multiply by a number greater than 1 or less than -1. If we're going to compress the graph, we are going to multiply a number between 1 and 0 or between -1 and 0. Again, if you multiply by 0, it just gives you that straight horizontal line. Okay, these ones you can work through on your own to get some instant feedback and help. Something I did want to show you here. Okay, so for number 1, what is the graph? What is the equation of the blue graph? Okay, well, first off, you can see that this graph here has moved down, right? It has moved down. So, and it's moved down by 1. So we know immediately we're going to subtract 1 from our original parent function. And the parent function for this guy is our x cubed. All right, so immediately we know it's not going to be letter D. We know it's not going to be letter D. All right, then we can see that it looks like our graph has been compressed. Our graph has been compressed, so it's no longer A. And I personally don't like that they did this for your options. They gave you 2 options that are both compressing, that are both moving down by 1, and I personally think it's very difficult to tell the difference between multiplying by 0.2 and multiplying by 0.5. All right, so there's 2 things that you can do. All right. First thing, as always, as we like to point out, you can plug in values. So when you're stuck between 0.2 and 0.5, pick a couple values, right? Plug them into both graphs and see which one matches up most closely, right? So you could see this is about, if this is 1 and this is 2, this is about maybe 1.8. So figuring out which one of these would get you closest to 1.8 if y equals 0. All right, so you can do that and work backwards like that. The other option you can do is if we pull back up our calculator here, all right, you can actually plot all of these on your graphing calculator, okay, and you can see the equations that I have. So the blue one here is your parent function, all right, the blue one there is your parent function, and then I have 0.5 as the black function and the 0.2 as the red function there. Okay, apologies. Okay, and then what you can do is you can actually look, and you all have options as well. So on your calculators, it should say y equals, right? You should be able to select on a single graph here and be able to type in y equals 0. Right, and hit enter, and then it would bring you over to a graph, and you could try to match up the graphs as best as possible. Okay, and what you're going to notice here is that the graph should be option B, all right, and that's solely based on, I plugged in a couple values here, and I matched it up as closely as possible to about that 1.7, 1.8 value when y was equal to 0. Or you could say you matched it up closely on the graph, either or, either option works. And I'm hoping that you don't get something this complicated where it's very, very similar. Okay, now if we look at number 2 here, what's the equation for the black graph? Okay, well, you can clearly see that this black graph got reflected across the x-axis. Okay, got reflected across the x-axis, and it is actually thinner than the original parent function. So that means we must have multiplied it by -2. All right, so immediately B is no longer an option. All right, so if we multiply by -2, that would have reflected our graph here and made it slightly skinnier. All right, Then the next thing you could have noticed was, well, the whole graph got shifted up by 1. Okay, so we're going to add 1 to the outside of our equation. So immediately we're at C or we're at D. All right, and then finally here the graph got shifted 1 to the right. So instead of having normal x squared, we're going to have x minus 1 squared. So by process of elimination, our final answer should be C there. Okay, and then this one is one that you're definitely going to see moving forward here. Okay, you have to know that this type of shape of graph is a quadratic, right? That y equals x squared parent function. Okay, so you can clearly see that it got reflected across the x-axis. Okay, and how I know that is because we go from having a U shape to having that upside down shape. So immediately right there, that leaves you with option B. Okay, but in case you needed to write this equation from scratch, we'll keep going here. So we know that our graph got reflected across the x-axis. So bare minimum, we know it's a -1, right? We know it's a -1 at least as this outside coefficient here. All right, then we know the graph got shifted up from the x-axis by 1. So it got shifted up, so we have this +1 here. All right, and then it got shifted 2 over to the right. And since it's 2 over to the right, I have to have x minus 2, right? So I got to go 2 over, 1 up, and it is flipped across the axes, okay? And I told you this number would be at least a -1, and how you could figure out if it's 1 or 2 is you could pick a couple points on the graph. So this looks like it's at 0.21, so you could plug this in and see, okay, if x is equal to 2, if x is equal to 2, is that going to give me y equal to 1 the way that I have it? And the answer should be no if this was a -1. So then you could try a -2, a -3. But it wouldn't be, hopefully, this too terribly difficult for you. Okay? So then moving forward here with the study sheet, with the study sheet, we'll go over the answers for that guy. So real quickly here, the main idea is when you stretch or compress a function, you change the shape of its graph, right? And how the graph changes, if you're stretching vertically, it's moving away from the x-axis, okay? And you can multiply the function by a number greater than 1 or less than -1, all right? If you want to compress, then it's also going to move it, but it's going to move it towards the x-axis, right? Kind of like you're squishing it. And you're going to multiply the entire the entire function by a fraction, right? So there's a couple examples here, and what that might look like is, again, you pull straight up here, you kind of push flatter down here, and those are just 3 basic shapes for a graph of x squared. All right, and then when you flip the graph over an axis, either on the x or the y axes, you're changing the location of the graph. So how that changes each point, if we flip across the x-axis here, the y coordinate switches signs, right? Okay, so if we're going across this x-axis, okay, the y coordinate will flip. All right, if we flip across the y-axis, that would be this guy, we're flipping this way. All right, and how that changes, okay? So in both cases, we're going to multiply, but we're going to multiply for the x-axis the entire function by a negative number. So it's going to be negative and then the outside of all the entire function. So you would carry that negative sign through all those different factors, okay? But if you are dealing with just flipping over the y-axis, you're only going to multiply every x in the function by a negative number. Okay, so effectively here, this 4 would not be touched by the negative sign, versus when it's here, it would be. All right, and we'll go over now, we'll go to a couple more problems here. Okay, so we're showing the different graphs here. So it says f of x is equal to x squared. It's stretched vertically by a multiple of 4 and shifted 1 unit down. Okay, so you know you have to multiply by 4, and then you're shifting 1 unit down, so you've got to subtract 1 from the end function. Okay, and then you should be able to, if you were asked to draw what that would look like, right, you should just be able to at least move that main point down and draw something that is skinnier with inside. Okay. Next one here, x squared is compressed vertically. Okay, so it's multiplied by a factor of 0.5 and it's shifted 2 units to the left. So remember, when we're shifting to the left, we have to have that inside the parentheses. So it's x plus 2, then that quantity gets squared. We're going to multiply that entire thing by that 0.5. Okay. And we're going to move forward here with the checkup. And just a reminder, you only have one quiz for this. So yes, you do have to do this quiz, and it's only on stretching functions vertically here. All right, so we'll work through a couple of these practice problems, but try to keep this short for time's sake. All right, so looking here at the 4.5 checkup. All right, so for the first 10 things, it wants you to look for the equation of f of x, okay, and looking at our answer choices. So if we didn't have these answer choices, it would be a little bit more difficult, but because we have them, we're going to use them here. All right, so we can clearly see that this equation for f of x has been reflected across the x-axis. So it's reflected across the x-axis, so that means it needs to have a negative value. All right, so clearly it's not that one because that's just x squared. All right, so if we were to reflect this across the x-axis, it would look like this. All right, it would look like that. But we then moved our graph up 2 units, 1, 2. So since we moved our graph up 2 units, okay, since we moved our graph up 2 units, we have to add 2 to our equation. All right, so it's not subtracting 2. And this one here would be as if we were moving it to the left. So the first answer choice is correct here. The first answer choice is correct here. All right. If we look at number 4 here, all right, so number 4. It looks like the graph is definitely skinnier than when it started. Okay, it's definitely skinnier graph. And you can clearly see that it has moved down and to the left. Okay, it's moved down and to the left. So we know that our graph is stretched and down and to the left. All right, so we know our graph has moved down 1, 2, 3. Okay, so we know for a fact by the end we're going to be subtracting 3. All right, and then immediately that crosses out all of our options except for the last one. But let's just verify to make sure that that matches. Okay, so we've gone over 1, 2. Okay, so since we've gone over, we need to have that x plus 2 factor inside our x component there. All right, so we have x plus 2, and then again, it looks like it's stretched, and it's stretched by that factor of 2. We could plug in a couple values and verify that, but for time's sake, we're gonna leave that alone. So that would be our final answer choice there. We'll skip 5 and 6 because obviously the graphs are a little bit cut off there. 4, 7. Okay, 4, 7. It says resembles the graph of g of x is equal to x squared. So we know that our original function looks something like this. Okay, and this is where you would refer to all the stuff that we learned today about what the parent functions look like, right? What the parent functions look like, where are they located, right? And for this one, it's got the origin is its vertex point at 0, 0. Okay, so we can count here. We go 1, 1, 2, 3, 4. It moved over 4, so right 4. All right, and then I'll color code this so we can make it a little bit easier. 1, 2, 3, 4. It moved up 4. So we moved right 4 and up 4. Okay. So our up 4 is going to be that plus 4 right there. Okay, so again, immediately all of these other options are out, but our up 4 is going to be that plus 4 right there, and then our apologies, I couldn't count right. Apologies, I couldn't count right. So this is actually up 1, 2, 3. Sorry, that's up 3. I don't know why I counted the origin. So that's up 3, and it's still right 4. Okay, so it's up 3 and right 4. So instead of having that plus 4, we need to have that plus 3 right there. Okay, and since we're going to the right 4, that means we're going to have that x minus 4 inside the parentheses. Okay, so apologies on that one. Okay, now for number 8 here, for number 8, again, our normal parent function looks like this. Okay, looks like that. So we can clearly see that it's reflected across the x-axis. All right, so it's reflected across the x-axis. We have moved over 1, 2, right? So we've moved right 2, 1, 2, 3, 4. So we've moved down 4. And again, I'm taking inventory because what that's going to help me do is it's going to help me narrow in on my answer choices. Okay, so I've done all of that, and then it does look like I have been stretched, right? It looks like it's definitely a skinnier graph there. All right. So for this one here, again, I like to go with looking at left and right first because that's the one I find the easiest. So if I've got to go right 2, okay, that means that my x squared now becomes x minus 2 squared. All right, so I'm left with option 1 or option 2. So option 3. So those are out there. Okay. Then the next thing is I have to go down 4. So both of them actually work for that one. They're both minus 4 at the end. All right, and then they both have a factor of which they could be stretched by, right? They have a number greater than 1 or less than -1. However, the difference between them is that this one is the negative value, and that negative value is what gets us to reflect across our x-axis. All right, and I will leave the rest of these for you all to work through. But again, that's the process. And whatever process you choose is totally fine as long as you get to the same endpoint. So again, I've walked through a couple of them, but you got to figure out what works best for you to be most successful.